Welcome to the next video, everybody. Today, we're going to get into the proof of the, let's say, commutative algebra portion of Weyl's main theorem. So we're going to be looking at the two criteria from the last video that are used to show that R equals T. And so we're going to do some background information today only, and we'll start the main proofs next video. And we're going to have to talk about fitting ideals to do this. So let A be a ring and let M be a finitely generated A module with generators, let's say M1 through Mn. Take a map F from A to the N surjecting onto M. That'll be the A homomorphism defined by F of EI equals M sub I, where E sub I denotes the ith standard basis vector here in IN. So that's zeros everywhere except for a 1 in the ith slot. The fitting ideal, fit sub A of M, is the ideal in A generated by the determinants det V1 through Vn. What are these matrices V1 through Vn? They're column vectors V1 through Vn, just live in the kernel of this F here, okay? Evidently, fit AM is already generated by the det V1 through Vn, where V1 through Vn are in a fixed set of A module generators for the kernel of F. So you don't need to take all the determinants of all the matrices of all column vectors in the kernel. You can just take a generating sets, okay? You have to check, of course, that this definition is independent of the choice of generators M sub I that you started with. You can do that easily by induction. That's done in Cornell Silverman Stevens on page 345. Okay, so here are some basic properties of fitting ideals. All of the proofs are more or less straightforward. And what I mean by that is maybe they're not all like super easy, but they're all, I mean, there's no real like novel insights needed to prove any of these. Okay, so proposition 1, let's let A be a ring and we'll let M be a finitely generated A module. Then 4 things are true. The A fitting ideal of M is contained in the A annihilator of M. Okay. 2, for any A algebra B, the fitting ideal over B of M tensor B over A is just the A fitting ideal of M times B. Okay, and this dot here represents the, I mean, this makes sense, right? Because B is an A module, so you can actually do this multiplication here. 3, for any ideal frac A and A, we have the A fitting ideal of A mod frac A is just frac A. Okay, and then 4, for every A module N, the A fitting ideal of M cross N is just the A fitting ideal of M times the A fitting ideal of N, and this is a product of ideals here. Okay, so for a proof of these things, you can again see CSS, page 345. All right, so let's specialize a little bit here. If A is a principal ideal domain, so a PID, then by the structure theorem for finitely generated modules over a PID, every finitely generated A module M takes the form M is isomorphic as modules to A mod frac A sub 1, cross A mod frac A sub 2, cross blah, 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 cross frac A mod frac A sub S for certain ideals frac A sub I and A. If you take properties 3 and 4 above, fitting ideals that we just got done discussing, what this tells you here is that the fitting ideal over A of M under this setup, so we have a finitely generated module over a PID, is just the product of these frac A sub i's here. So it's frac A sub 1 times frac A sub 2 times blah, 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 times frac A sub S, where this product is, of course, as a product of ideals. So now let's specialize kind of even further. If A is a discrete valuation ring with maximal ideal M sub A, what this tells you is that the A fitting ideal of M is just that maximal ideal M sub A to the lengths, the A length of M as a module, okay? And of course, if you have like an infinite power here, we're just gonna set M to the infinity sub A to be 0, okay? So that's kind of like a more specialized situation than the general setup up here, because in this situation, all the ideals are powers of the maximal ideal, okay? So this is a nice formula to have. Let's switch gears for a moment and talk about the basics of Koszul complexes, because we're going to need those, a little bit of theory of those as well to actually prove the commutative algebra stuff we need. So let's let A be a ring, and we'll let V be A to the N, and we'll let F be F1 through F sub N inside V. Okay, so F sub I is like the ith copy of A here. For any A module of M and M greater than or equal to 0 an integer, let's set K sub M of F comma M to be the A homomorphisms from the wedge product over A of V M times to M, okay? For phi in k sub m of fm, we'll define d of phi or d phi in k sub m minus 1 of fm by what? Well, d phi, for it to live here, better be a map from, the m minus first wedge product of v with itself to m. So I have to tell you what d phi of x is as a map. We'll just say d phi of x is phi of f wedge x, okay? So this extra f here is what allows us to jump down from m to m minus 1, because we're moving down then from the mth wedge product of v with itself to the m minus first wedge product, okay? It's easy to check by basic properties of the wedge product that d squared is 0 here. And so this is these maps here, these d maps, they actually form maps between these km's that make these km's into a complex. Okay, and so we'll call the resulting complex k sub dot of fm to be the Koszul complex of f on m. So here's what it is. It's a little sequence here, 0 to kn fm, then you have to apply the d map that puts you in k sub n minus 1 of fm. You apply the d map again, that puts you in k sub n minus 2 of fm, and so on, until you get down to k sub 0 of fm and then to 0. Okay, so here's a complex, the Koszul complex of f on m. So here are some basic properties of Koszul complexes we'll need. We don't need that much. One thing you can check for, like, how does this behave with respect to like base change? You can check that k sub dot of fm is just k sub dot of fa tensor m over a. I think that's not very surprising at all based on basic properties of complexes and the tensor product. We can also check that k sub m of fa is a free A module of rank n choose m. This is kind of a basic homological algebra fact. Okay. Also, like, okay, so we have a complex, right? So we can talk about homology and stuff. So the mth homology group of k sub dot of fm is written h sub m, excuse me, of fm. For example, h sub 0 of fm, the 0th homology group, is just m mod im. This shouldn't surprise you if you've worked a lot with homology before. The 0th group is usually some stupid thing like this. What is I here? It's just the A ideal generated by the FIs, where the FIs were the coordinates of F, if you remember. Okay. So there's some basic information for you. Here's a quick little lemma that we'll need. So lemma, all of the homology groups H sub m of Fm are annihilated by this ideal I generated by the F sub i's. This is kind of a straightforward algebra thing. It's proven in CSS on page 347. Okay, and then the last bit of background we'll need before we get into stuff next video is a little bit of background on regular sequences. So we're going to say a sequence of elements P1 through Pn in a ring A is M regular, where M is an A module. Okay, if for any I equals 1 to n, multiplication by P sub I, so the ith element of this soon to be sequence, on M mod the ideal generated by P sub 1 through P sub I minus 1 times M is injective. Okay, so you take all the guys before P sub I, make your ideal out of them, look at it times M, mod out by that in M. You want multiplication by P sub I on that guy to be injective. Okay, so proposition 2, take F to be F1 through Fn and A sub n as usual, and let M be an A module. If the A ideal I generated by F1 through Fn, so these guys here, contains an M regular sequence of length n, so this like rank as a this like rank here, then H sub I of Fm is 0 as long as I is bigger than or equal to 1. So in other words, we have no higher homology at all. Okay, we have trivial higher homology. Again, this is pretty straightforward. You can see CSS page 347 for the details there. Okay, so there's kind of our, like, I'll call this like baseline theoretic background that we're going to need before jumping into some of the tools, Weil's 2 criteria for proving R equals T. We'll get into that stuff next video. Thanks for watching, and I'll see you then.